Hi there. I'm Wade Webster. I'm an assistant professor at North Dakota State University of Soybean Pathology. And today I'm going to be talking about using predictive tools to guide scouting. So first, let's introduce what a predictive tool is, okay? A predictive tool uses different models or mathematical equations using historical data to predict future outcomes. So one really great example that we commonly think about on a day-to-day basis is weather. Weather models are something that we check every morning when we wake up, either on our phone or through the news. And these all use previous information to predict what's going to happen in that day, right? When thinking about predictive tools and predictive models, there's a couple of considerations that we need to think about, okay? These are going to include the inaccuracies that are going to occur due to the use of these models. So just like thinking about weather again, these models are not going to be completely accurate. Just like if you wake up and it says it's gonna rain in the afternoon, this may not actually happen. And so just understanding that these tools are just that, they are tools, and that they do have errors associated with them, okay? Additionally, these tools can become very difficult to interpret due to their high complexity from time to time. So these are things that may lead to issues with acceptance of different predictive tools. However, there's some really great benefits to using these tools, such as being able to prepare for management practices in advance, such that if we know we need to make a fungicide application, and we can prepare that sprayer a day or two in advance instead of the day of when this predictive tool is telling us, hey, we need to go make an application. Additionally, when thinking about pesticides or fungicides, these tools can also help prevent the application of completely unnecessary applications, saving those inputs as well as the financial standpoint. Additionally, these models can lead to improved yields due to improved management of that crop, as well as increased profitability at the end of the season. So there's some really great examples of predictive models implemented in agricultural systems today. Some of these include, from an agronomic standpoint, irrigation and crop growth staging, and then from a pest and pathogen standpoint, being insects and different pathogens or diseases. When looking at irrigation models, one that stands out is called Soy Water, which is a tool developed at the University of Nebraska-Lincoln, led by Dr. Jim Speck. This model uses inputs such as the soybean variety planted, your GPS location, and the planting date. And this tool will then pull historical precipitation data, the soil type for that individual field that you're looking at, and it'll help determine the water status of that particular crop. It also helps to predict the growth stage of that crop, which leads into the water status, which can help guide producers of when to make irrigation applications, right? So this can help improve the management as well as increasing that yield at the end of the season. So there are, again, a limitation to this one, in which these models were developed only for soybean maturity groups from a 1 up to a 4.5. However, there are more regional irrigation models available throughout the United States. Then, thinking about growth stage models, there is one in particular that stands out, that's just called Soy Stage, which is developed at the University of Arkansas. Again, there are limitations to this as well, such that this tool can only look at maturity groups between a 3.2 to a 6.7, as this tool was only developed for the Mid-South and the Delta region of the United States. All right. This tool also can only predict the timing of 3 growth stages, so R1, R5, and R7 for soybeans. And then this tool can also predict a risk level for freezing during that early season, right after planting. Then moving into a pest standpoint for insects, insects are generally fairly similar in their response to the environment. Insects respond or can be modeled quite well using a simple growing degree days, but generally they respond to moderate temperatures. Many need wind events for long distance dispersal or migrations, and then low intensity precipitation events. If we do experience these high intensity precipitation events, we can see a decrease in their populations, leading to a lower risk level developing. One example here is called Insect Forecast, which is an online tool which predicts the development or the risk level of 5 agronomic crops of soybean and corn listed here below. This example here on the screen is showing a risk for soybean aphid on September 22nd of this past year, showing a moderate risk from Wisconsin over to northeast Nebraska and up through the Dakotas. And so these are updated on a regular basis to give recommendations of when these regions might see high insect pressures. Then moving over to a pathogen standpoint or disease standpoint, we need to consider that pathogens are a little bit more diverse in their response to the environmental conditions that they're exposed to. So every good plant pathologist always needs to consider the disease triangle, which is that in order for any disease to develop, we need 3 things to occur. Okay, we need the pathogen to be present, we need a susceptible host, and we need the proper environmental conditions. Okay. So 2 examples here of soybean are 2 different diseases, charcoal rot caused by the fungal pathogen Macrophyllina phaseolina, which thrives under hot and dry conditions. Conversely, Phytophthora root and stem rot caused by Phytophthora sojei thrives under cool and wet conditions. All right. So this goes to show that we cannot develop predictive models or tools for the same or across different diseases. So now that we've introduced these tools, let's think about how do we get these tools into farmers' hands and how do we get them integrated into their systems. Okay, so currently there have been many forecasting models that have been developed over the years, but their adoption has been quite low. And there's a couple of different reasons for that, all right? Some of them being that looking back in time, we needed very specialized equipment to be out in the field to make these recommendations or to have very high quality regional weather stations available. Recently, with improvements in equipment, we are now able to make more high quality predictions of weather data, leading to the less requirement of that specialized equipment out in the field. We can also see an issue with there being too many prediction tools available, such that if you have one crop and you have 5 different tools that need to be implemented to manage that crop, it may just become too much of a burden to handle all of these different tools where you abandon all of them altogether. Some extra methods of integrating these into production systems here is demonstrating to the farmers the benefits of these predictive tools and providing accurate predictions on-farm trials, uniform fungicide trials across different universities and different regions, and then demonstrating the yield differences and yield benefits to using these tools, validating to these producers that these tools can benefit them in their systems. Another way to integrate these effectively is to keep the apps and these interfaces of these tools quite simple. The more complicated they get, the less likely they are to become accepted by the users. In this case, we like to use the rule, it's called the cup of coffee rule, in which anybody using a tool should be able to get their recommendation in the amount of time it takes for them to drink a cup of coffee. All right, so you want to sit down, get your recommendations, know what you're going to do for the day in a matter of 2 minutes or so, roughly. And then also the integration of these tools into smartphones, such that everyone nowadays typically has access to a smartphone or a smart tablet, in which that they can make these recommendations from their hand within only a few seconds. Again, going back to that cup of coffee rule. So some really great examples of different applied predictive modeling tools. So these are only looking at diseases and pathogen models, are the wheat fusarium head blight or fusarium risk tool, which is shown here on the right-hand side. This is a web-based application which helps to show the risk of fusarium head blight developing within different regions of the United States. So this example here is from March 18th of this past year, showing that there are regions around the Gulf and the East Coast, the Southeast coast, showing that there's high levels of Fusarium head blight developing, which may recommend a fungicide application. Two additional applications, which have been developed into smartphone apps, are called Sportcaster, which is looking at soybean white mold, and then Tar Spotter, helping to predict tar spot on corn. And both of these, Sportcaster and Tar Spotter, I'll walk through with a little bit more detail. So first, let's just introduce white mold as a disease and go through the disease cycle, as this is important within the predictive modeling. Okay, so white mold does persist as sclerotia, or the overwintering structures in that topsoil of the field. During the season, these sclerotia will then germinate to form little tan mushrooms, which we call apothecia. These serve as the inoculum source. Okay, so this is what we will be targeting for our predictive models in the next couple of slides. Once these apothecia are formed, they release puffs of ascospores into the undercanopy of that crop. And these ascospores will then infect this flower tissue. And these flower tissues will serve as a nutrient source for these spores, initiating that infection, leading to yield loss later in the season. So I want to again emphasize this point, in that the flowers need to be present in order for infection to occur. At the end of the season, sclerotia are then formed and released back into the field at harvest, continuing the disease cycle in the next year. So there's some predictive tools and predictive models that have been developed focusing on sclerotinia, or white mold, right? These, like I mentioned earlier, predict the development of these apothecia in this picture on the bottom left-hand side of the figure. And these were developed at the University of Wisconsin by Dr. Jamie Wilbur and Dr. Damon Smith. There are two different models depending on the irrigation status of that particular field, and these equations are listed here in the upper right. These include the weather variables of maximum air temperature, wind speed, and relative humidity. All right. And so this figure on the bottom right here shows an example of Hartley, Iowa in 2019. This black line here gives a risk probability for each individual day throughout the growing season. And then this yellow line bar across is demonstrating an action threshold, meaning that if that risk probability reaches above that action threshold, this is when we say you need to take action and you need to make a fungicide application. I've added these arrows here to indicate when that soybean crop is in flowering or flower structures are present. So between the R1 and the end of the R3 growth stage, so the beginning of R4. And we can see that in this particular location, we did not see this risk probability reach above this 40% action threshold. All right, so in this case, no fungicide application was recommended. So these models were developed into a tool called Sportcaster, like I mentioned, and these give daily risk levels for that particular field. So on the right-hand side of this image of a phone, we see that the risk level is at about a medium level at 28%. And this helps give recommendations for when to make these fungicide applications in a very simple and effective way. Okay, so far these tools have shown to have about 80% accuracy. So let's take a look at Sportcaster and just walk through the setup of that app. All right. So this is the interface. We want to set up a new field. All right. So let's click on the location, scroll over to a region of Wisconsin just north of Marshfield, Wisconsin, and we'll tap on the screen, enter that GPS coordinates, and then type in the name of that particular field. All right. From there, we're going to enter a couple of different conditions on that field. So what row spacing was it planted in, and was this irrigated or not? So 30 inches, and it was irrigated. Then again, we're going to look at flower structures. Are those flowers present? We're going to click yes. And then row closure. And we have this great tool. We can assess whether or not this is under the threshold or over the threshold, depending on canopy closure. And so we know this is over. And we're going to pretend that today is July 15th of 2022. Okay. So we're going to set the date. We're going to run the model here. And we're going to see in this particular location in Marshfield, that the forecast is running low. We're saying that there's low risk of disease developing, so we're not going to make a fungicide application. Okay, so let's go back to our field list here of all the other fields that we've have an interest in, and we can actually click this map button on the bottom to look at this across the entire Midwest. And let's go to this one in North Dakota, in Oaks, North Dakota. Okay, let's assess this one again. We know flowers are present, and we know row closure is being met. Now let's again look at July 15th of 2022 and look at this risk level here. So we run it and we see in this location, we're running high. So here we would make a fungicide recommendation, okay? So this is a great example of two different locations showing different risk levels for this particular tool. So to validate that model, let's look at the actual uniform fungicide trials that have been performed across the Midwest. So this data here is taken from two trials in 2022 from both Michigan and Wisconsin, looking at similar fungicide trials or fungicide treatments comparatively to a non-treated, right? So when we look at this, we're looking at both disease data, so the DIX, disease severity index, and then yield in the yellow bar. So I've highlighted this red box here on the right-hand side. This is the non-treated, and you can see that this treatment or this non-treated here has one of the highest disease levels as well as one of the lowest yields. Conversely, looking over on the left-hand side, we see this green box here encircling two different treatments, both using Endura. The one on the left-hand side is a 2-pass program, both at the R1 followed by the R3 growth stage. And then we have another treatment using Endura using our Sporecaster applications or Sporecaster recommendations, okay? And in this particular case, Sporecaster was only applied one time. So we can see a similar trend here that, you can make 2 applications of Endura, or you can make 1 application at the appropriate time and receive about similar yield and disease levels. Additionally, here's another box showing a single pass of Endura at only the R3 growth stage. Again, showing that there's a slight improvement when using Sporecaster comparatively to a 1-pass program at that R3 growth stage. Okay. So now we've covered white mold. So let's jump into tar spot. Okay. So tar spot is a relatively new disease that has been developing across the Midwest, and is caused by a fungal pathogen called Phyllochora matus. Okay. So again, thinking about the disease triangle, this tar spot pathogen persists in the stover of the previous year's corn crop on the field over winters, and then in the next season in the spring and summer, this pathogen release spores and inoculum into the under canopy of that crop. This inoculum will lead to disease development, causing these tar spot looking lesions, as well as these fisheye looking lesions in the top figure here, which resemble the eyes of fish caused by a necrotic ring around these tar spots. As the season goes on, if environmental conditions are conducive, then disease will develop to a level high enough for premature plant drying down, as we see in the bottom figure here. This premature drying will lead to yield losses due directly to this pathogen. So like I said, this is a new and developing disease here in the Midwest. Tar spot was first identified in Illinois and Indiana in 2015. And as we can see through this map, each progressive year, the pathogen and disease has been able to spread further and further from the original locations. Okay. So when thinking about modeling, we are needing to use these environmental conditions. And this is all work performed out of Mexico, where the tar spot pathogen originates from, which is showing that we need moderate temperatures between 63 and 72 degrees on an average basis across an entire month for the development of tar spot to occur. And then we also need high moisture variables. Okay, so 4 out of the 5 important variables seem to be driven by moisture, such as high levels of relative humidity, long durations of leaf wetness, many days of high fog and foggy days, as well as a large amount of monthly precipitation, okay? So again, driving home that moisture seems to be important. To reiterate that, in 2019, this is a really, really great example of a field of corn that was all applied with headline AMP at the beginning of Silker R1. And you can see right around that center pivot where irrigation was applied, that this corn crop has started to dry down directly due to that tar spot pathogen, okay? When we get outside of where that pivot was hitting with irrigation, we see that crop is still green and it's still filling the grain, leading to increased yield relative to under that pivot, which is going to experience decreased yield in that particular case. So again, it's just driving home the point that it seems that moisture seems to be highly important for this disease in one way or another. So in order to manage tar spot, we developed an app called Tar Spotter, which is using the similar framework to Sportcaster, as you can see in this image here, with different weather variables and a few different inputs, such as fungicide and the current growth stage that it is in, as well as irrigation status that has been applied in the previous 14 days. So again, this tool will help guide producers of when to make fungicide applications. And I'll note that the current version that is available at the moment is using previous year's data, but there are big improvements that are being made currently, which will hopefully be released prior to the 2023 season using one of the largest data sets that we have acquired yet. And so that data set, just to briefly introduce that here, just to show that we are making large improvements to these models. So this is a map here showing all of the corn producing regions of the United States, taken from USDA data showing acreage of corn across the US. We can see the darker green each of these counties are, the more corn that is produced there. And then there are small dots, red and blue dots, indicating red dots are the small research plots trials that we took data from. And then blue dots indicate commercial fields that we went out to and scouted on a regular basis, collecting data for the development of these models and improvements of these models. So up to this point, this seems to be the largest tar spot data set that we have, improving our confidence in these predictive tools and predictive models that we have for the basis of tar spotter. So again, validating that these tools and tar spotter is highly effective. So again, this is based from 2021 trial based out of Wisconsin. So again, not using this newer version that we are developing, but previous year's versions. We can see that this here is showing across the entire season. This red bar on the bottom indicates the non-treated, showing the greatest development of disease over the entire season. And then there are 3 products that seem to be highly effective at controlling and reducing tar spot development: Herbis Neo, Delaro Complete, and Veltima. However, you see at the very top, if we use Veltima in coordination with tar spotter recommendations, so applications in this particular case, and this is different for each field, but in this case, applications at the V10 as well as the R2 growth stages, then we improve and reduce the development of tar spot even further. So this is showing that disease progress through the entire season. 3 different ratings were taken at the growth stages of R3, R4, and R5. We can see at R3 on the far left-hand side over here that we do not have any disease and very little disease developing at this point. But as we go to the end of the season here, we see that this blue bar or blue line on the very top indicates the non-treated, indicating disease severity greater than 35%, which is leading to premature drying down. But if we look on this very low gray bar here on the right-hand side, we do see that's the Veltima using our tar spotter recommendations with ear leaf severity ratings of less than 5%. Okay, so this is incredibly promising to see. This is a really great example of showing this visually. So this left-hand side is showing the non-treated controls, where the right-hand side is showing where these tar spotter applications were made. Okay, and you can see the left's drying down, and we're going to see severe yield losses on that left-hand side relative to the right-hand side, which is going to be able to continue to fill those grains throughout the next couple of weeks. To kind of wrap this up here, I just want to mention, we have two of these apps, Sportcaster and TargetSpot, are currently available. But what we've been able to do is develop another app called Field Profit, which kind of serves as a one-stop shop where we can look at all of our predictive models that we have currently available here. And hopefully in the future, we'll be integrating more of these apps into this tool so that you can go in and enter locations for one field, looking at multiple different diseases for that field. All right. So this is kind of looking forward into the future, and more things are to come. So with that, I really want to thank you. I hope you all have a really great season ahead for this 2023 growing season. You use these tools to guide scouting. Remember that these are not perfect, that these are going to be something that can assist you in your scouting endeavors. And I would be remiss if I did not mention these funding sources for helping develop of these tools. Foundation in Food and Agriculture Research, the Wisconsin Soybean Marketing Board, the Wisconsin Nutrient Pest Management Program, and the Wisconsin Corn Promotion Board. If you have any other questions, please let me know. Shoot me an email or message me on Twitter. And thank you very much, and good luck.